All right, stat students, let's get to some conditions for sample proportions. So first set of questions that we have here on this first section, let's talk about what's going on here. So we have this scenario where we're talking about Reese's Pieces. So go grab your candy if you have it. And we want to look at how do we use sampling proportions to describe a population. That's all this is about, okay? So the company states that the orange Reese's Pieces make up 50% of the full production of all Reese's Pieces, okay? So we're going to imagine taking simple random samples from a machine and look and see if that lines up with the population. All right. If I were just in general to take one sample of 25 here, what would you expect the number of Reese's Pieces would be that you would get? Well, if we think that the population proportion is 50, we would expect in that one sample to get 25 times 0.50, which is 12.5. Okay, that's the expected value. That's actually this formula here, EX, the expected value. So let's actually do some sampling. The first sample we got in this part B gave us 13 candies that were orange. So out of the machine, we got 13, which is 52. If that was the only sample we got, I would predict that the real proportion of orange Reese's Pieces is 52%. But do we really want to just go off of one sample? Probably not, right? There's going to be variability in our samples. There's different things going on. So let's scroll down and actually expand on this. Okay. So what's going on? We've got a situation here where we took 10 samples, right? All of sample size 25. All right. These calculations, class, were done by a computer. So this is all done in some simulation. Okay, so that's where we get these numbers. They were right here. And then we get these outcomes, okay? If we're describing shape, remember shape, in this case, is probably pretty uniform with one peak, okay? We're looking at the distribution. Number 1 and 2 are asking about what type of measurement did we use for center and what type of measurement do we use for spread. Well, in this case, we got a value from our mean, but the symbol is not just any old mean, it's the mean of our p-hats, and p-hats are sample proportions. So we would say for center, we took the mean or average, they use the word average, of our sample proportions. It's important to be able to know that symbol. Spread was standard deviation. That's what they use for spread, but it's not just any old spread, it's the spread of p-hats here, which is the standard deviation of our sample proportions. So I'll do ST for standard, DEV for deviation of sample proportions. So we're bringing in that concept and that context here. That's proportions. Okay. So pay attention. We're going to keep using that symbol here throughout. So we want to make sure that we understand it. So those are the types of measurements that we're talking about when we're describing the distribution. Okay. That's the thing that you have to remember whenever somebody asks you to describe the distribution. So let's go down to D and E and take a look at those here. So I made a note here about the difference between C and D. If we look at C, we took 10 samples. That's 10 SRSs, simple random samples of size 25 candy. So each sample had 25 candy. right? In this case, we have 500 samples. We have 25. So there's an increase, right? In Part D, they took 500 samples, which is more than the 10 that they took in C. I underline more than because when we compare things, you want to use that kind of descriptive language. It's not enough to just say that one had 500 and one had 10. You actually have to, I know it's obvious that 500 is more than 10, but you actually have to say it. So that's the difference between D and C. Now let's take a look at the difference between D, which is this guy again, and E. So if we read through, right, sampling distribution, we change the machine dispense to N equals 50. N is sample size instead of 25. So in E and D, we now have samples. We still have 500, right? That's the same amount of dots. So if I were to look at both this one and this one, we would have the same amount of dots, 500 total. But in each of those dots comprise a different number of samples. In D, there's 25. In E, there's 50. So we would say that part E has a larger sample size. $50 instead of 25, right? So there you have it. And what ended up happening with that? Well, if we note that now I have a parameter of 0.50, right? That's what we started with. That's P of 0.50. And our sampling distribution centered now at 0.50 as well. So it lines up. We have a unbiased parameter or unbiased estimator. That's what that says. Okay? Because our sample means, the means of our sample proportions is the same as our parameter, the population outcome. So increasing that sample size gave us a better estimator. And it became less variable as well. Notice that the standard deviations are different as well. In part D, it's 0.098. In part E, it's 0.068. So a larger sample size, less variability. And there you have it.